Hello, I'm Dr. Aizaz from MedicoVisual.com, and in today's visual lecture, we will talk about the Davenport diagram, and it is also called pH nomogram. So this is the diagram that I am talking about, and you might have seen in your textbooks. Almost every famous textbook has this, including Guyton and Hall, the textbook of physiology. So to really understand this, what I will actually do is that I will build it from scratch with you, and we will build it together, and along the way we will properly understand that how exactly does it work. And it's very easy actually. So I will start a new diagram, new drawing, and let's start working on it together. So basically, it's a simple graph, and it's not actually a simple graph. It's slightly complicated, and let me show you what is going on with this. So what we will actually do is that we will start drawing this, and let me okay, let's start drawing this, and on x-axis as well, let's draw the x-axis, then we will label it as well. And of course we will be drawing it from scratch. So it starts from 7.0, then there is 7.1, then 7.2, 7.3, 7.4, and let's make it further longer, and then let's say 7.5, 7.6, 7.7, and 7.8, up to 7.8. And then here we will start from 0, then we will go to 5, 10, 15. I know this lecture might sound boring to you, but believe me, this will really hammer this concept of Davenport diagram in your mind. And if it feels boring, no worries, you can watch it on a bit higher speed, but please definitely watch this. Or better yet, try creating this with me. I will also use Microsoft Excel in this video, which I think most of you people must be having. So it would be better if you create it with me actually. So 45, 50, 55, and 60. It's a bit too much bigger. Let me zoom it out a bit. Now actually, how can we draw the graph on this? To draw the graph, we need to understand a few things. Okay, let me tell you by the way what is these x-axis and y-axis. This is the pH, right? This is the pH, and here is the HCO3 level. HCO3 level in not mmHg, in milli equivalent per liter. Yes. So now how can we calculate this? Now according to the pH, as a function of pH, we can write the HCO3, and to do so we can use the Henderson-Hasselbalch equation. So what is the Henderson-Hasselbalch equation? pH is equal to pKa plus log base, conjugate base, over acid. Now in our case, in case of the major buffer of our blood, which is the bicarbonate buffer, we write the base is actually HCO3 negative, and the acid is H2CO3, but we can replace it with 0.03, which is the solubility coefficient of CO2, and we can write it PCO2. We have discussed these things in previous lectures, so I'm not repeating those details. I am a bit speeding up here, but I hope you can understand these things. So pH is equal to pKa for this buffer we know is 6.1 plus log HCO3 over 0.03 into PCO2. Now, for every point in pH, we want to ask that, okay, let's suppose if we reach up to 7.1, we need to ask that what would be the bicarbonate level to reach the pH 7.1. Then on 7.2 we will ask the question again that what would be the bicarbonate concentration to reach the pH of 7.2, and so on. That's how we plot the graph, any graph per se. So actually we need to find out the HCO3 negative, and to do so we will have to rearrange this equation. Well, how can we do this? I think first of all the important thing is that we need to get rid of this log. So how can we do so? First of all, let's rearrange the equation and let's write pH minus 6.1. Let's bring it here. Mathematically, how it is going on? Mathematically, I can minus 6.1 here, and I can also minus 6.1 here. This and this will be cancelled out. Then we will remain with pH minus 6.1 equal to log, like this equation, like this. I hope you can understand this basic algebra. I know many medical students and even doctors are bad at mathematics, but I am trying to keep it bare minimum. Now, to get rid of this log, we need to take antilog, and antilog is 10 raised to power something on both sides. Why it is so, you can watch my lecture on the concept of the pH, and in that I have briefly described it, and in other lectures as well. So if I take 10 raised to power this, so this part will be cancelled out. So what will be remained? 10 raised to power pH minus 6.1 is equal to HCO3 negative over 0.03 into PCO2, like this. Now actually we are looking for HCO3. To find out the HCO3, we can multiply it by 0.03 into PCO2 at both sides here as well. 0.03, I think I said 0.02, sorry about that, it's 0.03 into PCO2. Now you see here we are writing it, multiplying it, so these values will be cancelled like this, and in the end we will get HCO3 is equal to this part of equation, or we can write it like this: HCO3 is equal to 0.03 into PCO2 into 10 raised to power pH minus 6.1. Now let's start at 7.1. Now the question is that at pH 7.1, what would be the HCO3 level? Or in other words, we can also say at pH, not at pH, at HCO3 level of 5 milli equivalent per liter, what would be the pH level? So we can start from here and draw the graph, or we can start from x-axis. We can start from y-axis or x-axis, it's up to you. But I will start from the pH actually. Now, oh yeah, by the way, if you start from the HCO3, you wouldn't even need to do all this interconversion. You could have just put the values here and you would have got the result. I think I have made it slightly more cumbersome, but anyhow, this is how we learn. So HCO3 negative. Okay, now how can we get the value? Okay, so for pH 7.1, I can write 0.03 into PCO2. Now what would be the value of PCO2? The normal PCO2 is 40, so for now we can write 40 here. I will tell you that we actually create multiple isobars, and then we will take a shortcut in Excel later, but first you need to understand the basics. Then 10 raised to power pH, we are trying to find for 7.1 minus 6.1. Now we can calculate this, and to do so I will be using the scientific calculator by decimals. So 0.03 into 40 into 10 raised to power 7.1 minus 6.1, not 6.1. Okay, so yeah, I think this is correct. So the answer is 12. So on 7.1, our answer would be 12, which would be somewhat here. Yes, somewhat here, like this. So let's put a dot here like this. Then for 7.2, it would be 15.1. So 7.2, 15.1, somewhat here. Then 7.3, it would be 19.01, so nearly 19, somewhat here. Let's put a dot here. Then 7.4, it would be 24, about 24 actually. And then 7.5, it would be 30.14, somewhat here. Yeah, somewhat here for 7.5. Then 7.6, 30, nearly 38. So yeah, somewhat here. Then 7.7, 48, somewhat 48, nearly 48, somewhat here. Okay. Then for 7.8, it would be about 60. Yeah, a little bit higher than 60. So somewhat here. Now if we connect these dots, we can actually connect these dots. Oh, by the way, what about pH 7.0? That would be 9.5. So it would be somewhat here. Yeah. So now we can connect these dots. And yes, oops. So we can get a line like this. So that's how we got a single line. Now we can also calculate it for different PCO2 value. So we can calculate it for 0.03 into, let's say, 45, and also lower. So I can replace the value here, 45, and then this would start from 10.7, somewhat here. Yeah, 10.7 would be somewhat here, so I can start it from here. And then actually I will have, if I put all the dots, I will have a bar like this. Then for 45, yeah, then for 50 I will have a bar like this, and I can create multiple bars. And actually to do so, in less time, we can actually take a shortcut, and we will do so. We will use Microsoft Excel for this. That would make this much easier. So here I have Microsoft Excel, and let's start working on this. Let me zoom into it. So our first column would be pH, and pH would start from 7.0, then it would actually 7.01, 7.02, and 7.03. Of course, I'm not gonna write all these. I will do like this, select all these. Of course, this is not an Excel tutorial, so I might skip over some of these things. I am not teaching you Excel, but I am trying to teach you that what exactly is going on here. So this is the column for pH. Then actually we can create these bars, these so-called bars. These are called isobars, or there is some other name as well, very complicated name. I can't even pronounce that, and I won't even try to. I forgot it anyway. So we can create then an isobar for different values. Actually we should actually start from 10, then 15, then 20. So after like 5 units difference, we can bring it up to like 120. Now you will see the power of Microsoft Excel, how quickly it will draw the graph for us. We will use the Microsoft Excel formula here, and the same formula. The thing is that the reason I taught this thing before, so that you understand what is going on in Microsoft Excel. If I had simply opened up Microsoft Excel in front of you, I know most of you would be confused. So same formula, 0.03 into PCO2. Now PCO2, let me first write PCO2 here. This is the wrong approach, of course, but then I will tell you what is the correct approach. 10 raised to power icon is this one. Then yeah, it is telling me that the formula is wrong, but Excel, don't worry, I will fix it. And pH is 7.0 for now, minus 6.1. Now of course here we know PCO2 is 10, so we can write 10 here, right? And then we can copy this formula, right? And then actually I am teaching first the wrong approach. So then here we can change the value of 7.01, right? Then again here I will change the value. Here I will look, it's 7.02, so here I will write 7.02, and I will repeat this thing until I reach the row number 82, right? Wrong. I am just joking. Don't try to do this. It's a wrong approach. Actually, this is the power of Microsoft Excel formulas, that we can grab these values as a sort of variables. So here is the PCO2 value. We can select this and then click here, and it will get the value from here, right? Then for pH value, here's the 7 is the pH value. We can replace it. We can click here, and it will grab the value from here. And actually, the interesting thing is that as I pull this formula down, then it will not grab the pH from this cell. It will grab the pH from the cell which is below it. So this is the power of this. You see, it will, when I grab this, it has actually pulled everything correctly. I hope so. Yeah, I think so. No. There is one other problem that is here, and I knew this problem, it would be there, and I wanted to teach you. The other problem is that it is also grabbing the PCO2 from the wrong cell. So initially, you see, for this cell I selected B1 as this cell, B and 1. This is B1 cell, this one. I selected B1 for the PCO2, but for when it moved down, then it selected the B2. You see, it selected the B2, this one, this one is yeah, it selected this blue one, B2, the one below it for the PCO2 value. So that is why it got the wrong value. So actually I want to teach it that it should not change the what it is called, the row, right? To do so, I will put a dollar sign like this. Is this PC2? Yeah, I will put a dollar sign like this, so it would work. Let's see if it is working or not. Yeah, apparently it does work. Now the problem is that if I pull this formula here, now you will see another problem. Now it is grabbing the pH value from this column. So again, I have to teach this Excel formula that it should keep fixated on this column. And to teach this, I will simply add dollar sign before A. Again, I did not intended to teach you the Microsoft Excel in this video, but anyhow, I am still doing it. Now I can fill all this space and it should work. And it does. Yeah, it does actually work. And now it is just time to create the graph. Let's select all this. And actually let me delete this pH thing because it causes a problem with the graph sometimes, so I will just delete it for now. So now we will go to insert, and here I will go to graphs, and from here we have the scatter graph, and here I will select this one, the scatter with smooth line. And here we have a very nice graph. Oops, very nice graph, and we will label it properly, no worries. Okay, so now we have this graph, and actually the axes are a bit off. The pH should start from 7 and end at 7.8. To do so, I will click here and right click, and I will click format axis, and I will start from 7.0 and make it end at 7.8. Yeah, this should work. And also now I will format this axis as well. It should start from 0 or 5. 0 would be fine, I think. And it should end at 60. Yeah, now we have a very nice canvas to do our work further. Yeah, I think it's cool. Now I want to do something else as well. You see in the background the graph paper is very wide apart, so I want to change that also. To do so, I will go to add chart element and grid line, and I will add minor ones here as well, minor ones. And I think it should work, but 1 2 3 4 5, this is cool, but I think this what is this bicarbonate level, it should like follow 0 to 5 to 10 to 15 and so on, rather than these bigger jumps. I think we can improve this one as well. So let's go to here, no, not here, to the format axis again, and here the major one should be like 5 and minor one should take 1. I think this should work. Yeah, and it does. 0 5 10. Oh yeah, it is working fine. 2, 3, 4, 5. Yeah, it is working fine. And also, how about this one? Should I change this one as well? Okay, minor one should be 0.01, and major one should be like, yeah, 0.01. This is cool, I think. So we have like 7.57. Yeah, this is fine, I think. This is cool. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5. I think this is cool. 2, 3, 4. Yeah, I think this is cool. So this is the baseline grid that we have created already. Now you see each bar represents, let me make it bigger. So you see each bar represent an isobar of PCO2. So this one is for 10. If PCO2 was 10, let's suppose, then if PCO2 was 15, then if PCO2 was 20, and then 25, 30, 35, 40, this one is normal, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, 105, 110, 115, and 120. So this is the baseline that we drew. Now actually we can move this to our beloved tool. What is it? Can I make it even bigger? Yeah, this one is cool, I think. So now we can move it to our beloved tool concepts app, and let's bring it there. Okay. Okay, so let's bring it here for further manipulation. Let's make it bigger like this. Okay, so I can zoom inside. Now actually we can draw these what we call as the pathologies. Actually we can draw the pathologies on top of it, and I will teach you what is the basis of that. First of all, let me tell you what is the normal. The absolute normal is pH 7.4, and 24 would be okay, 21, 22, 23, 24. 24 would be the bicarbonate level, and PCO2 would be 40. Actually the secret is that if we only know the two values, it would automatically coincide with the third value. You see, if we know it's 24 HCO3 and we know that pH would be 7.4, it would coincide here at the 40, the PCO2 level of 40, you see. So this is the absolute normal, but of course normality is not always absolute. It is actually a range. So if we talk about the range of the bicarbonate, it starts from about what is that, 20 maybe, or 21. Okay, so let's start, like draw a line here, somewhat here, 20, and ends at about 29 or 30 or 28 maybe. It varies according to different books, right? And of course the pH is from 7.3 to 7, not 7.3, 7.35. 1, 2, 3, 4, 5. So here to 7.451, 2, 3, 4, 5 here. So this is the range actually. Okay, we can draw like this. And then PCO2 varies normally between 35 to 45. So these lines actually, and 45 is this line. So we can actually draw the normal range in the intersecting part here. Let me show you. So the normal range could be somewhat like this. Somewhat like this, you know. Okay, I am not trying to make the most beautiful nomogram, but just to make you understand. So this one is the normal range. And I will keep this dot for the absolute normality. Now actually, if I draw something like this, and here as well, now understand that anything in this range should be, for the simple disorder especially, should be alkalosis range. It should be in alkalosis range, and anything, arrow should not be like this. I think it should be like this. And anything in this range should be, would be actually in acidosis range. Now it won't be like everything here would be alkalosis and everything here would be acidosis. It is a bit more nuanced, and actually there are certain rules that are followed that are called renal rules. And actually let me copy and paste it for you, and then I will teach you what is going on here. Give me a second. So here are the renal rules, and this table is from the textbook of Costanzo Linda, textbook of physiology, except this last line which is from CMDT. Costanzo Linda has this value 0.4, which is slightly off in my opinion. Actually, not my opinion. Most of the other textbook has this 0.5 value. Even the nomogram in most of the textbook, they follow 0.5 value, but 0.4 is not technically wrong, but this one is a bit more accurate. Yeah. So, and by the way, you might find some discrepancy in different textbooks. Like this is like 1.3 to 1.5 sometimes, but this is the one that is commonly followed. Now, where this graph comes from, that is the real question. Is there any formula, is there any mathematical equation that is used to calculate it, like Henderson-Hasselbalch equation? Well, actually no, that's not like that. It is based upon different experimental data and clinical data. You can read more about it online and on Google Scholar. I will not go into that debate, and I will discuss why there are some differences here. Let me talk about it briefly. The thing is that why is there difference here in metabolic acidosis and metabolic alkalosis? First, let me describe what is going on, what this table is telling. For the metabolic acidosis, what it is saying is that for 1 milliequivalent per liter decrease in bicarbonate, there is also 1.3 mmHg decrease in PCO2. Let me show you on graph what is going on. So it is talking about what? It is talking about metabolic acidosis. So acidosis is on this side, right? So we are starting from 7.4. What it is saying is that, and this PCO2 is 40, this line is PCO2 40. Now it is saying that if I follow this line like this, and you see the bicarbonate level is dropping, and it is going on and on. You see bicarbonate level is dropping. So actually acidosis won't be like that it would follow this line like this. Actually what will be happening is that along with this, here we are assuming that PCO2 is constant at 40. It is not constant normally for metabolic acidosis. It is not constant. Our body would try to compensate. And how would our body try to compensate? If bicarbonate level is decreasing, it means alkali reserve is decreasing, it means acidosis is going on. So it means to compensate for this acidosis, our body will also try to get rid of acidic gas, that is CO2. So CO2 level would fall. So it won't be like this, rather it would be somewhat like this, and I will show you exactly how it is, right? It won't go in line like this, it would go downward, because you see, if we go downward, the PCO2 level is decreasing. I hope you can understand this graph correctly, right? So how much would this decrease? This would decrease for every one HCO3, 1 unit HCO3 drop, there would be 1.3 unit drop in PCO2 level, loss of acidic gas CO2. And if we talk about metabolic alkalosis, here this would be opposite. In metabolic alkalosis, the alkali reserve HCO3 will increase, and to compensate that, the acidic gas will also increase. But here you try to understand the difference. In metabolic acidosis, there is very sharp decrease or fall in PCO2, but in metabolic alkalosis, there is very little increase in PCO2. Why it is like that? Well, the reason is that how do we get rid of the PCO2? Well, it's very simple. We can hyperventilate, we can breathe quickly and deeply to get rid of PCO2. And how can we retain CO2? Well, it's very simple. You don't breathe. Well, actually, you cannot stop breathing. Otherwise, your O2 level will sharply fall. So you can hypoventilate, you can decrease the rate of respiration, but it is limited. Understand this, listen it very carefully. You can hypoventilate, but it is strictly limited by the development of hypoxia. You cannot stop breathing, or you cannot hypoventilate for too long, or for too excessively, too overzealously, right? Overeager. That is not possible, because you might even die with the hypoxemia, which of course our body does not want. So that is why you can relatively easily get rid of CO2, but you cannot relatively easily increase PCO2 without risk of developing hypoxemia. So that is why this difference exists. Unfortunately, you will have to sort of memorize these values, but I think you can look at this a few times, and it's easy to memorize this. It's not very difficult. But anyhow, then moving to respiratory acidosis. Now this is acute, mean it is like a very little time has just passed, and of course it's natural that there won't be a significant increase in HCO3 if very less time has passed. It's very logical. And then after some time, when the renal compensation starts, then there would be of course increase in HCO3 and in alkalosis as well. But you see, there is 0.1 unit difference in respiratory alkalosis and respiratory acidosis. I hope you can appreciate that. Why is this difference? Why this difference exists? Well, actually, to be really honest with you, I don't know. But a logical reason could be, now it's more of my speculation or my own hypothesis. The reason might be that, of course, actually the kidney, if I draw the kidney, simple nephron, now to reabsorb. So actually what is actually happening, that bicarbonate, almost all of the bicarbonate is filtered across the Bowman's capsule into the Bowman's capsule along the across the glomerulus, and it comes here. Now it would be not normally, I should say, if kidney does not do something, it would be lost in urine. So kidney has to actually actively reabsorb the bicarbonate through different mechanisms that we have already discussed, right? So to bring the bicarbonate in, I mean, to increase the bicarbonate level inside the blood, it is an active process that has to be done by the kidney. But to make the bicarbonate simply lost, to excrete the bicarbonate simply in urine, your kidney does not need to do anything, right? It would just let it go, so it won't need to actively do something. So do you think it is easier to get rid of bicarbonate and to decrease bicarbonate, or is it easier to increase bicarbonate in blood? Decrease or increase? Think about it. Of course you would say it is relatively easier for kidney to get rid of bicarbonate and hence decrease the bicarbonate level in blood, and here it is being reflected. So decrease in HCO3, you see, decrease in HCO3, which is required in alkalosis. You see, that is relatively more efficient, you can see here, as compared to increase in HCO3. You see, it is relatively less efficient. So this is the whole idea. Now actually we can complete this Davenport diagram or nomogram using these renal rules, and I will show you how we can do that. I think first let's remove this diagram to make up the space for rest of our discussion for today. Now let's start from the metabolic acidosis, that I've told you that it won't be going like this. This is first of all wrong approach. Now we can actually start from 24, and okay, let's do something. The renal rule for metabolic acidosis is that 1 milliequivalent per liter decrease in bicarbonate must be equal to 1.3 mmHg decrease in PCO2. Now it's cumbersome to do it for every level, every 1 unit, so I can take a shortcut. What if I multiply these by 5 on both sides? So now it would be 5 milliequivalent per liter drop in HCO3 is equal to, how much is 1.3 multiplied by 5? Let's open the Desmos. Where is that? Yeah. So 5 into 1.3, 6.5. So it is equal to 6.5 mmHg decrease in PCO2. Now we can use this rule, this modified rule, which is just an extension of the actual rule, to draw our graph. So we will start from 7.4 and 24. Now from 24, if we come to 21, then you would be thinking that actually if I come to 24, I can put a dot here, and then I can put the dot here on 14, and again this would create a graph like this, a line like this, which is not compensated metabolic acidosis. Normally the metabolic acidosis, alkalosis, or other pathologies, acid-based pathologies, they must be compensated, right? So to compensate it at 24, actually how much drop it would be? It would be 6.5. So rather than me putting a dot here, I should put a dot at here is the 40, here is the 40, and here is the 35. So 5 unit drop. Then if I write like 6.5 unit, that would be, you know, somewhat here, yeah, somewhat here like this. So I can put a dot here. So you see, we are following this 24, this is 24, we are following this line like this, and here at this point it is coinciding at PCO2 value of drop in 6.5. I hope you can understand what I am doing here. So I have put a dot somewhat here. Then further we go 5 units, that would be 14, this line, and here if I write, if I see about 6.5 units drop, so somewhat here would be, I think somewhat here. It is not going to be accurate. Of course, to make it accurate, we can actually do this in Excel as well. But I deliberately, I am doing it on this concepts app to make it a bit more intuitive and easier to understand. It is more complicated when we can do it on Excel, but that would become like more complicated than this. So it's easier here to draw a rough estimate. So then at 9 unit, it would be somewhat here. Then at what is the after 9, that would be like 7, 8, 9, 4. Yeah, that would be 4. So that would be, I think, somewhat here. Yeah, I think yes, this is correct. So we can connect these dots like this. Oops, yeah, so we can connect these dots. I think it's correct if I'm not wrong. Let me confirm this. I think the fourth one would be, the other dot would be somewhat here. So again, it's not completely accurate, but yeah, you can get some idea that what it actually is representing. So we can make a line like this. Now actually understand one thing. Understand this, that the compensation, as Dr. Najib says, our body has not read the books. So compensation is not always going to be perfect. There would be some degree of variation. The central line is like a perfect compensation, but it would actually look somewhat like this. In a real world, actually, it would look somewhat like this, and actually the nomograms or Davenport diagrams that are in your books, it covers most of the most of the cases, and actually they have drawn it like from data, not formulas. They have drawn it from actual data, patient data, but we can draw it using the formulas as we are doing it right now to make you understand. Now, how about the metabolic alkalosis? For metabolic alkalosis, we have this rule that 1 milliequivalent increase in HCO3 is equal to 0.7 mmHg increase in PCO2. Again, we can multiply by 5 and 5 here as well. So it would be 5 milliequivalent increase in HCO3 would be equal to 0.7 multiplied by 5. What it would be? 0.7 multiplied by 5, that would be 3.5 mmHg rise in PCO2, and we can draw the graph with it. Now actually we are starting from 24. We can go to 25, 26, 27, 28, and 29. So 29, that would be like 5 units. Right? So if we reach 5 unit, it won't be the PCO2 won't remain 40. It would actually rise like 3.5 units. So here if I do the dot here on this brownish line, that would be 5 unit jump, but it is not 5 unit, it is about 3.5 unit. So 3.5 unit would be somewhat where it would be like somewhat here, yeah, somewhat here. Then further I can go 1 2 3 4 5 5 units right here, and of course then further 3.5 unit jump would be there. So that would be somewhat here, right? And then 1 2 3 4 5 here again, 3.5 unit rise somewhat here, 1 2 3 4 5 here again, 3.5 unit somewhat here, and then 1 2 3 4 5. So this would be somewhat here maybe. Then 1 2 3 4 5. Now this would be somewhat here. Then 1 2 3 4 5. This would be like somewhat here. So here we can connect these dots to create the compensatory line, the ideal compensatory line for metabolic acidosis. Not acidosis, sorry, metabolic alkalosis. And of course, word is not ideal, and so is our body. So there would be actually some range here like this. So this is the line to represent the metabolic alkalosis, right? So this was about metabolic alkalosis. Then let's move forward to respiratory acidosis, or as some people call it, respiratory acidosis. So that is 1 mmHg increase in PCO2 means 0.1 milliequivalent rise in HCO3. So actually we can multiply it by 5, so that would become 5 mmHg increase in PCO2 would be equal to 0.5 milliequivalent increase in HCO3. So this is the acute respiratory acidosis. So let's start it from here, and okay, so we are talking about respiratory acidosis, so it means the HCO3 level is rising. So if there was no compensation, this would be like a straight line like this. So actually, because even in acute cases there is some compensation, so rather than putting a dot here, and we can actually put a dot at halfway level like this, then like this here. I think is it correct? No, I think this one is wrong. Somewhat here, then half a unit, then again here, then here, then here, 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 and in this way here, here, here. here, and I think up to here is enough. So this is the acute respiratory acidosis. We can connect these lines and we can draw like this, and of course it's not perfect always. There is actually a range. So this is acute respiratory acidosis. How about chronic? For chronic, we have this rule that 1 mmHg increase in PCO2 means 0.4 milliequivalent rise in HCO3, and 0.4 multiplied by 5 would be, I think, 2.0. Let's confirm this. 0.4 multiplied by 5 would be 2 units. So every 5 units rise in PCO2 would be 5 unit rise in PCO2 would be 2 unit increase in HCO3. It's very easy. So start from here, and at here we would be having 2 units rise, then here 2 unit rise, then here 1, this is 1 unit, this is 2, so 2 unit, here also 2 unit, and 2 unit. Okay, 2 unit would be here, here, then here, then here, here, and here, 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 and I think that was all. Let's write it here. Okay, now again we can, this is the ideal, we can create this line like this, connecting these dots, and we can draw like this. Roughly like this. This is acute respiratory acidosis. This is chronic respiratory acidosis. Now, what about the acute alkalosis, respiratory alkalosis? So 1 mmHg, let's write 5 mmHg decrease in PCO2 would be 0.2 into 5. 0.2 into 5, that would be 1 unit decrease in HCO3. So let's draw this. So start from here, and actually if we talk about 5 unit, that would be here, so there would be how much? 1 unit. So 1 unit is here, then 1 unit is here. Let's zoom it a bit. Then 1 unit is here, then here, then here, and I think that's all. So we can connect these lines. Oops. And again we can draw this. I don't know what went wrong with my drawing. So roughly I can draw like this. Actually, it's a bit narrow for the acute changes. It's a little bit narrow like this. A narrow strip would be like this. Acute respiratory alkalosis. Yeah. How about chronic? For chronic, we have this formula: 1 mmHg decrease in PCO2 is equal to 0.5 milliequivalent decrease in HCO3. We can multiply 0.5 by 5, so that would be 5 here and 2.5. So we need 2.5 here. So here is the 40 and 1, 2. Okay, it's too congested. Let's remove this so that I can see what's going on. So it's here, center is here, center is here. Yeah, so 1, 2 and 2.5 would be somewhat here. Then 1, 2, this is 0.5, 1 and 2, it is 2.5 here. Then 1, 2 and 2.5 would be here, somewhat here. Then 0.5, 1.5 and 2.5 would be here. And finally 1, 2 and 2.5 would be 1, 2, 2.5 would be somewhat here or here. Yeah, this one is accurate quite. Okay, so we can fill this. Let's make a narrow strip here. Like this. And this is chronic respiratory alkalosis. So wow, we have actually created our Davenport diagram or nomogram. Actually, it is filled like this. I can quickly fill it for you. So it's actually filled here. If you want to make it more accurate, we can fill it like this. Now, what is the power? What is the use of this Davenport diagram? The real power lies in the fact that I can put the values of any of the pH, any of the case of any of the sample of ABGs actually here, and I will just put its value on this graph, and I will get to know exactly which disorder is there. And for mixed disorders, it would be like somewhere in between. Let me show you some example, and then you will realize the real power of Davenport diagram. Okay, first, for example, let's suppose that okay, let's use this color. Let's use a black dark color actually. So for example, okay, so let's suppose that I tell you that I give you a report, and on that report there is okay, there is PCO2 is about 32, and pH is about 7.3, and okay, and it is like HCO3 is about 15. So if I ask you what is the diagnosis in terms of acid-base disturbance, you can actually plot here 15 and 7.3. It would be somewhat here. Actually, its value should be, I think, 14. So it would come somewhat here. Yeah, somewhat here. It would be like somewhat here. And here you can see it is in the metabolic acidosis range. Similarly, I can draw the point anywhere, somewhat here, 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 or wherever, and you will exactly know that which disorder is this, right? It's very easy, right? So this is, by the way, metabolic alkalosis. Now the real power of this lies in the fact that we can actually diagnose the mixed acid base disorders through this Davenport diagram very easily. Well, how come? Actually, let me tell you some scenarios, then you will be able to understand its real power. So one example is that okay, let me write it here. pH is 7.39. pH is 7.39. HCO3 is 14 mmHg and PCO2 is 24. Now, what is this disorder? Apparently, pH looks normal, so you may say that it is normal. Well, actually, it's not normal. If you look at the values, normal here is 22 to 28 or 29. You see, it's very low. And PCO2 is 35 to 45. Again, it's very low. So, HCO3 is low, so it means it is from ideal 7.4 pH, it is 7.39, so it is likely the HCO3 which is driving it downwards, right? So actually, to really understand this, we can mark it here on this. So it's 7.39. 7.39 would be here. And then what is the other one? It is HCO3, which is 14. And actually, just from these two, we can plot this. But for your understanding, let's consider the 24 as well. That is here. 25, little bit lower than 25. This would be somewhat here. Yeah, here. So here, if I no, for something to be normal, not something, I mean the pH ABGs to be normal, if I draw the dot, it must lie somewhat in this range. Even that could be deceptive. I will show you in a moment. But generally speaking, if the dot lies somewhat in this range, it is most likely normal. Of course, not always. I will show you an exception as well at the end. But here you see it is lying outside this range. It is lying between metabolic acidosis and respiratory alkalosis. So it is most likely, just putting this point, you can understand that this is a mixed acid base disorder with mixed what elements we have: metabolic acidosis plus we have respiratory alkalosis. What is actually going on? We do not need this Davenport diagram actually, but it makes your life easier. In exam, you might not be given this Davenport diagram, so I will teach you how to do this without this Davenport diagram, but that will take a little bit longer. And to do so, we can actually use the Renal rules. For that, the algorithm is that we will need to first look that from where it is deviated. Is it like lower than 7.4 or higher than 7.4? I'm talking about pH. So pH is a little bit, although very little bit lower than 7.4. So it is 7.39. So it is more on acidotic side. So which is bringing it towards acidosis? This is bicarbonate, the alkali reserve, which is low. It's not that PCO2 is higher, the acidic gas, it's not higher, right? So actually it is, one thing is clear, that there is metabolic acidosis. But is it truly metabolic acidosis? For that we will have to see the compensation, the degree of compensation. For metabolic acidosis, here it is, there would be 1.3 mmHg decrease in PCO2. So how much decrease in PCO2 is here? So HCO3 normal level is 24, so we have 14. It means how much, we have 10 unit drop in 10 unit drop in HCO3 levels. So if we multiply 10 by 1.3, which is ideal compensation, we can use calculator for that. Even we don't need this, but still I am doing it. That would be 13. So it means normally it should be 40. 40 minus 13, it should be up to 27, right? But here it is even lower than 27. It is 24, 3 unit lower than 27. So body does not usually overcompensate, but because here there is overcompensation, it is, we know that it is not, it won't be likely an overcompensation. Rather, there must be something else which would be decreasing the CO2 level, and that something else is the respiratory system. There might be some hypoventilation, not hypoventilation, hyperventilation, that would be getting rid of acidic gas. So that is why it is not just metabolic acidosis, but respiratory alkalosis as well. So next, if I go to another scenario, that would be, okay, let me write it for you. pH is 3.0 and HCO3 is 18, and the third is PaCO2 or PCO2, that is 38. Now pH 3.0 is actually 7.3. It's not even possible to have this much pH and be alive. I made this grave mistake here, but anyhow, so it is towards acidic side, and you see alkali reserve is low. So one thing is for sure, we have metabolic acidosis here. And even if we do not use the Davenport diagram, we can use the renal rules, and 10 multiplied by how much is the okay, 24 minus 18, 19, 20, 21, 22, 23. Okay, let's use the calculator. 24 minus 18, 6 multiplied by 1.3. So 7.8 unit should be the decrease, 7.8. So it should be 32.2 unit decrease in PCO2. But here we have 38. It means PCO2 is high. It means something is causing the rise in PCO2, which is the respiratory acidosis. So we have respiratory acidosis plus metabolic alkalosis, and we can very cleanly verify it using our beloved Davenport diagram. So 7.3 is here and HCO3 is 18, that would be here, and the third matrix is 38. Okay, so this would be where it is, so it would be somewhat here, yeah, somewhat here. So here you can see it is between metabolic acidosis, it is between metabolic acidosis and respiratory acidosis. So our diagnosis is confirmed metabolic acidosis plus respiratory acidosis. Next, we can move to another scenario where we have, okay, let's write the scenario here. pH is equal to 7.55 and HCO3 is 33 and PCO2 is again 38. So we can simply mark it on the Davenport diagram, and PCO2, okay, it's 7.55, so somewhat here, and then it is what is the HCO3? 33. 33 would be 31, 32, 33. It would be here. We can follow this, and we can follow this one as well here. So it is here. Now it is between the metabolic alkalosis and respiratory alkalosis. So it is just simply by plotting on this Davenport diagram, we know that it is a mixed metabolic alkalosis plus acute respiratory, or not acute, just simply we will call it respiratory alkalosis. Metabolic alkalosis plus respiratory alkalosis. And actually we can verify this with renal rules as well. If you do not have this Davenport diagram with you, we can verify with the renal rules. So pH is high and HCO3 is also high. It is up to 28 or 29, but it is more than that. So it means this is deriving the pH high. So how much would be the PCO2? For this is first of all metabolic alkalosis confirmed, because alkali reserve is high, plus what else we have? Metabolic alkalosis rule is that we have to multiply the difference with 0.7. How much is the difference? 33 minus 24, and we will multiply this value with what? 0.7. So 33 minus 24, 9 multiplied by 0.7, 6.3, 40. It is alkalosis. So it means there should be a rise in the PCO2. It should be nearly 46.2, close to 46.2, right? But here it is 38, right? It is not that much close. It means that something is actually decreasing it, and because something is decreasing it, we will think about the hypoventilation, not hypoventilation, hyperventilation. Body is getting rid of PCO2. So that is why it is respiratory alkalosis. So here we can write respiratory alkalosis. So this is confirmed also with the renal rules. It's very simple. For the last one, I think I won't be applying the renal rules. I think you can understand this. Lecture has already become very long. So I will just plot it on Davenport diagram, and it is your exercise. You can apply the renal rules yourself if you want to. So for the last scenario, it is pH is 7.4 to 0.2 unit higher than ideal one, 7.4, and HCO3 is 42 and PCO2 is 67. So 42 would be 1 to here, and 7.42 would be here. From top it would be here, and 67 would be somewhat here, right? So we can follow all these, and our graph would be, where it is, yeah, it would be pointing to here. So it is close to chronic respiratory acidosis, but not very close. It comes to lie between the respiratory acidosis and alkalosis. Yeah, so it is between metabolic alkalosis and respiratory acidosis. So it's a mix of metabolic alkalosis plus respiratory acidosis, right? So this was all. And then wait for the final boss. Now this is going to really confuse you. And I would be really happy if you... Okay, first let me write the scenario here. And for this, I would give you a little bit more information. This is difficult. pH is equal to 7.42. And bicarbonate is equal to 25. And PCO2 is equal to 40. Now, some extra information that I would give you here, that is sodium is 140, chloride is 95, and yeah, what else? I think that is all. Now, if we point it on Davenport diagram, we can do so. 40, okay, 7.42 would be, we have already marked it for another scenario, and the other thing is 25, HCO3 25, that is here. We can follow this, and it is here. Okay, now you would be saying, okay, Dr. Aizaz, it is perfectly normal. No acid-base disturbance is there. Why waste our time? Just write normal in diagnosis and that is all. Well, not so quick. It is the final boss of the game and it is not so easy. Here, we also have these two values, and actually, we can calculate the anion gap from that. I have discussed anion gap previously. I will not do it in this video. So to do so, anion gap, sodium minus chloride minus bicarbonate. Sodium is 140 minus chloride is 95 minus bicarbonate is 25. What would be the result? Let's put it here. Sodium is 140 minus 95 minus 25. That would be 20. So anion gap is 20. Anion gap should be nearly 12, or it would be maximum up to 16 maybe. So here it is like touching 20. It is not touching, it is actually equal to 20. So here in this case, actually anion gap is high, and anion gap actually depicts the unmeasured anion. And what are the unmeasured anion? An example could be, let's say, lactate. Now where is lactate coming from? So if we have, let's say, lactic acid and lactic acidosis, lactic acid would release H positive, which would be buffered by our buffer, bicarbonate buffer for example, and it itself would be converted to lactate, which would increase the levels of unmeasured anion in our plasma, which would lead to increase anion gap. So increase anion gap almost always indicate an underlying metabolic acidosis. So it means there would be metabolic acidosis. But on top of that, bicarbonate level is normal. Why it is so? Because here is the bicarbonate. Something is trying to pull it towards lower side. It is like stuck in a tug of war, and other thing is pulling it towards higher side. So the other thing is metabolic alkalosis. So this is actually a scenario of metabolic acidosis plus alkalosis. Now, this scenario seems very tricky. The reason being that there is no history or other useful data that is being provided here. But in reality, actually, it won't be that much difficult. You would have a proper clue in your question. This could be a scenario of, let's say, uremia or acute renal failure. In acute renal failure, there is often the acidosis, metabolic acidosis, and this patient, unfortunately, of acute renal failure developed vomiting plus vomiting. Now, you know that in vomiting there is loss of acid, so there is metabolic alkalosis plus metabolic acidosis from renal failure. So you can have this clue, and on top of that you have this data, and you can confirm that it is a case of metabolic acidosis and metabolic alkalosis. Especially for undergrad medical students, the mixed disorders, they do not usually pop in your exam, and if they do, that would be relatively easier scenario. That won't be very difficult one. But I think I have trained you for the complicated ones as well, so that you can really solve them. I think that was all for today. Thank you so much for watching this video. Have a great day. Goodbye.